right, this is your very last bit of notes, the last little bit of information that we're going to go over. And this goes way back to chapter 10, and we're going to model nonlinear data. So we're basically going to do nonlinear regression. Okay, and you don't know exactly when you're going to do this. You probably start out thinking you're going to do linear regression. You're going to write a y equals a plus bx, or as the AP Stats exam writes, b0 plus b sub 1x. So that's what they use instead of a and b. So the number in front of x is the slope, and the other number without a variable is the y-intercept. And so what we typically do, we look at a scatter plot for data, and we're going to look at a scatter plot for individual baseball salary in millions of dollars for various years between 1980 and 2001. So just a little bit of information first. When statisticians look at a scatter plot, they often use the phrases signal and noise. The signal is the underlying form of the data. All we have dealt with so far is a linear form. If you recall, there are many other forms of data, basically forms of an equation or the picture that you could graph. So you could graph all kinds of things, from quadratic, which would be a curve up or down, a U or a hill. You could have cubic form, which would be just a couple of waves like this. You could have logarithmic form, which rises quickly and then tapers off. You could have exponential form, which just rises very quickly. So there's lots of different forms that you could have. And so the signal is the underlying form or shape that the scatter plot makes. And the noise is the random variation from that form. So you might have a scatter plot that really definitely shows a pattern like this, an exponential pattern. But there's an occasional point that's kind of flitted off, and that's the noise. So those are variations from that pattern. Okay, so or that one point that's kind of right here that might make it appear like it's a more linear relationship. So we've got signal and noise. So, for example, when we studied the relationship between fat and calories in hamburgers, we saw that hamburger with more fat has more calories. That's the signal. The more fat you have, the more calories you have. Fat goes up, calories go up. But even hamburgers with the same amount of fat can have different amounts of calories. So the signal is more fat, more calories. More fat, more calories. Both go up. Okay, directly related. But that there's the same. Here's an amount of fat down here, and it can have. And you can have a hamburger with all the same amount of fat, but different calories. So that's the noise. So the residual plot is really the key here. So if the residual plot looks randomly scattered, then our model has captured the whole signal and only the noise remains. If the residual plot shows a pattern, however, then our model has missed some of the signal and we should seek a better model. So back when we did linear regression, we checked the residual plot. The residual plot should be randomly scattered in order for a linear model to be appropriate. If we're trying to decide whether we use a different model or a linear model, we look at the residual plot. The residual plot is the most important thing to consider when deciding which model to use. So we've got some data to show the highest individual baseball salary in millions of dollars. I have entered this into two lists. Now, a little note. These numbers represent years since 1980. So this represents 1980, and this 1982, and this 1989. So what we do, we shift the data on the x-axis so it is closer to the origin. So if we had these numbers instead of 0, 2, 9, 10, then we would be way, way far away from the on the x-axis, we would be way out here at 1,980. So we want it closer to the origin. We want our scatter plot to be closer to here. So we come up with a way to rewrite these. So we just use basically, if 1980 is the first year we're looking at, we call that 0, and then so forth. And then millions, we also kind of want to be close to the y-axis, the 0 on the y-axis, the origin. So instead of changing these to millions, please don't do that. Just leave it as that means 1 million, 2.04 million, 3 million, 4.7 million. You shouldn't have to change things to millions when you see it. So that's why we're just going to use these numbers. So in other words, 17 means 1997 because it's years since 1980. So I'm going to make a scatter plot of this data with a least squares regression line. And I'm actually going to, I have it right on my calculator, so you're going to do a scatter plot. So second stat plot. And turn it on. I want a scatter plot. And I'm just going to graph it. And I want to zoom 9. And I'm pretty sure that line on there shouldn't be there, so I need to go to my y equals, I need to clear that out. Now I'm going to go and I'm going to do stat calc. I'm going to do linear regression a plus bx with my lists. I'm going to store my regression equation in vars, y vars, enter, enter, and then I'm going to calculate it. And so it gives me that the least squares regression line, it's actually right here, is negative 2.128 plus 0.8904x, and this happens to have an r squared of 0.7429 and an r of 0.86. So r, the correlation, is the amount of scatter from the plot. It's the strength of the linear relationship, and this is the variability in the salary that is accounted for by the year. So this is our scatter plot, and if I go back to second stat plot and graph that, I've also got the linear regression line in there, and it's okay. But then the thing is, I look at the residual plot. So now what I want to do is I want to go to the stat plot, and I want to look at my residual plot, which is also a scatter plot. So to get your residual plot, you're going to do the x's with the residuals, which, since we already did the stat calc 8, it's already there. So I just need to go to second list and just go down to the names, and if you go down far enough you'll see resid, and that's what I put. So I want to graph the current x values with the residuals. So then I just hit graph, and I want to zoom 9 this. And of course, I've still got that line shouldn't be there, but this is the residual plot. And that residual plot really is, it looks like it has a pattern, like it's got this kind of a pattern here. Okay, it's got more of a curved shape. It's not very randomly scattered. I've got little clusters around here. So there is an obvious pattern here. So it's clear that our model has not captured the signal of the data. That is, the model doesn't have the right form. So this linear regression is not the best. So in general, there are two approaches for finding models for nonlinear data. So what we need to learn to do is exponential and logarithmic regression. So two things, two ideas, schools of thought in fitting our, we could fit a curve to the data, or make the data straight and fit a line. Okay, so we are not going to fit a curve to the data, we are going to make the data straight. So for several reasons, the second method is preferred in AP statistics, although in the real world, option 1 is often preferred. To straighten the data, we can employ all sorts of transformations. We can square root, we can find the reciprocal, etc. In AP Statland, our transformation of choice will usually be the logarithm. We can use either the base 10 logarithm, the common log, log, or the natural logarithm, ln, and get similar models. In general, we will use the natural log, since this is what most statisticians prefer. But you should be able to use both. It's just a difference of a button on your calculator. So the original data seems to look like exponential growth, meaning, okay, we've got the original data back here, and exponential growth starts out growing slow and then grows very quickly. Sorry, you couldn't see that. So exponential starts off growing slow, and then it looks like it's starting to pick up speed here and grow faster. So it looks like it's an exponential model. So let's take the natural log of the salaries. So we're going to take the natural log of the y. So we're going to make a scatter plot of the year. So we're going to have the year versus the natural log of the salaries. So what I would do then, I would go back to my data, stat, edit, and up in the heading of this, I'm going to take basically the, and maybe I want to do that in list 3. So I have something new. I want to do the natural log of list 2. And so now what I'm going to do for my scatter plot is I am going to do list 2 for a scatter plot, or list 1 with list 3. And I'm going to graph that. And I actually want to do linear regression on this one. So I would do stat calc 8. And with list 1 and list 3 this time, store my regression equation in y1 and do the calculation. So this time, and this is all worked out here, this time I've got, this is my equation. I took the natural log of the y's, okay? So my new model, instead of just having y, it has natural log of y equals, there's our A, there's our B. If I look at my scatter plot, with my line, it looks really pretty nice. Okay, this one just looks a little more slanted, but they're the same line. If I look at my residual plot, I want to graph this with the residual plot. So there's my residual plot now. It does look quite a bit better. It is much more scattered. I've really spread it. Instead of having clumps, I've still got kind of a little clump here, but it does look much nicer. So our new model, models in this form are called exponential models. So when we take the natural log of the y's, they're called exponential models. And you could rewrite them if you took this equation and you rewrote it as an exponential. You could rewrite it as a y hat equals a times b to the x, which you don't need to do. You just leave it just like that. Okay, so the residual plot still shows a possible U-shaped curve. I've still got that here. Maybe not so much, but it's kind of, I mean, it's just, you still got that blob there and still slightly curved. Okay, so it's much more scattered than the linear model. So thus the exponential model would be more useful than the linear model. Remember, there's no perfect model, but some are more useful than others. So we would like to use this model to predict the highest salary for the years 1993 and 2005. Do these seem reasonable? So we're going to have to use this equation, the natural log of y equals 0.13 plus 0.136x to predict the highest salary for the years 1993 and 2005. So 1993 would mean that is when x equals 13. So when x equals 13, I put that in here, so the natural log of y equals 0.13 plus 0.136 times 13. So I'm just going to go back to my main screen and take 0.13 plus 0.136 times 13, and then I've got the natural log of y equals 1.898. Now I do need to get y by itself, so what I need to do is I need to rewrite this as an exponential function. So the natural log's base is e, so this will be e to the 1.898 equals y. The answer to a log is always a power. So then I'm just going to go e, whoops, clear, second e raised to the 1.898 power and get 6.67. And we'll finish this on the next video.